Thanks very much to the iStructD for giving me this opportunity. This project was a work of love for me. I could call it my all-time favorite project, at least to date. To be able to both design and build something like this. It was kind of like a real-time experiment where I got to test a whole bunch of engineering ideas and have them come together into something beautiful. First, I want to thank the Lord for his beautiful creation and this wonderful opportunity. Also, many thanks to the client, the town of Banff, and the Nancy Pauw Foundation for entrusting this project, which is so dear to them, to us, and what a location. Okay, a little bit of an outline of what we're going to be talking about today. Go over the location of the bridge, some background, procurement method, the client brief, the various schemes that we explored and the one that was chosen, talk about conceptual design, then get into the nuts and bolts of structural analysis and modeling, which was a key part of this project, and then get into construction on site and the prefabrication process. And then finally, erection day, and talk a little bit at the end about vibration. So location and site. This is a gorgeous town for anyone who's been there. It doesn't matter the time of year. It's in the heart of the Canadian Rockies, and it really is the guardian of Canada's first and most coveted national park, Banff National Park. Location here, just in the border of British Columbia and Alberta, Western Canada, and in the mountains. The glacier-fed Bow River flows through the town, and which is also very closely guarded. Banff gets more than 4 million visitors annually. It's one of the most popular tourist spots in North America. It's a hiker's paradise. There are walking and cycling trails everywhere. It sounds like I'm giving a sales pitch for the town of Banff. What they call active transportation. There's so many trails to enjoy. You see here in the center next to town is the old road bridge. Now, that was the only bridge crossing this river for well over 100 years. And there are numerous activities, including the Banff Springs Hotel, a famous hotel, and so on across the river. And they weren't able to realize another crossing to more recently. So in 2013, we actually designed and built for them another bridge. You see here, the Bow River Pedestrian Bridge in 2013, just downstream from the road bridge. But the bridge I want to talk about today was named the Nancy Pauw Bridge after she passed away. She was an avid cyclist and resident of the town. And it's located at a bend in the river next to the town. So here's the site. There's a large bend in the river. The water slows and the banks here are very low. 110 years ago, the town architect had in mind across from Central Park, adjacent to town center. In fact, there was an attempt in 2007 to make the crossing, but there were technical challenges and it didn't proceed. In the meantime, they needed to carry new sewer and water lines across the river at the downstream site, and we were able to carry those under our 2013 footbridge. There it is. And this was the year of the great flood of 2013. In fact, the waters have subsided a little here. They were up encroaching the wood at the high point. It was like I think they called it the 300-year flood. This was an 80-meter span also, but it was a propped cantilever, and here we're putting in the keystone. It's also in a beautiful setting. In fact, I got the photographer to catch my wife and I walking across it, and this photo is mounted in my office. It is my second favorite project. But the vision for a crossing at Central Park remained. And it is in an even more prominent location. It needed to be even better. And there were a lot more challenges as well, structurally. The environmental scrutiny had only grown since the first bridge. And so we had Parks Canada and the town scrutinizing everything that we were doing. But they wanted the bridge to be graceful, unobtrusive, and natural, fitting the spectacular surroundings. The town architectural guidelines called for wood and stone. Steel was allowed, but not preferred. Project was procured through a design-build competition. There were 5 respondents, and we were awarded in May 2021. This was a team structure. We worked directly as the design-build contractor with the town and hired all the consultants and subcontractors. We were also the engineer of record and performed the engineering in-house. The client brief. As I said, he wanted a natural solution, but it was a near impossible task, especially the low profile that they wanted. But the client saw the glint in our eye that we weren't going to be put off, and he didn't relent either. So the wood and stone is their motif in the town of Banff. They wanted it to have minimal impact, obviously, a clear span if possible, no structure above the deck, a maximum of 5% slopes, minimal intrusion into the parks on either side, and what they say permeable to elk. In other words, not hindering the prevalent elk that actually walk right through the town at times. And it needed to be dark sky compliant. And what we'd experienced with the other bridge, it was getting up to 10,000 crossings per day, and they expect even more on this one, or expected. Here you see the site, town to the northeast. It's right adjacent to the main street of the town. It's just like a 3-minute walk from the junction here, the street here. The rec grounds to the southwest rather, and the road bridge, which is just off the screen to the right. A closer view of the site. Note the minimal berming. That was crucial to the client. We offered 3 schemes to the client. All clear span, 80 meters, structure below the deck. The challenges were significant with the low banks. It implied an impossibly slender solution with enormous thrusts. These are the 3 schemes, the timber, a tapered steel box girder, and a hybrid, and they chose scheme 1. I wanted to show a few examples of historic stone arch bridges, which are, have some similarities. The stonemasons had to wrestle with similar constraints, clearing the river adequately, yet not requiring people to climb a mountain to get across. But they took forever to build. So here's the scheme that the client chose. The timber is the primary structure. In fact, they asked the simple question of us, what could be more fitting than a wood beam on stone supports? Here, we wanted to use a very different natural material. How to mobilize the axial stiffness and also get some fixity at the abutments, just like the stonemasons did. But we weren't allowed to touch the river, and no centering was allowed. In the competition, here's what we sold them. But now we had our work cut out for us. How on earth we were going to deliver the perfection we'd promised? And it was right in the middle of COVID, where costs were escalating, and we were on a fixed price, and supply chain issues were emerging. But the idea was to touch lightly, an incredibly shallow arch with almost zero environmental impact. Could we deliver on this? Talk some more about the concept. This is the basic structural diagram. Tapered shallow arch pushing against stiff abutments. Just like the European bridge designers trying to keep the bridge as high above the water for as much width as possible in an elliptical shaped profile. You can see it in the way we step the glulam. Tuck as much curvature as possible into the ends where, like the early stone bridge builders, we sought extra stiffness to assist the arching action and capture the fixity. We needed very stiff abutments, and reliably so, to ensure snap-through buckling wouldn't be an issue and that the vibrations could be managed. And we needed a good geotechnical engineer. So I actually pulled him out of retirement. He was the one who helped me with the first bridge. Here you can see the whole thing. The tapered glulam girders and what we call the haunch, made of weathering steel, which supports the girders and helps anchor to the concrete abutments, supported by the pile caps and piles. We're going to do a little structural test. So we built a scale model. I just wanted to feel the stiffness of the shallow arching action. It's useful to do scale models from time to time. But here you get the idea. We needed to bring the thrust down as low as possible to the abutments to give the greatest rise to the arch. And we didn't want to submerge it, so we carried the profile down with the haunch. But we also thought, could we not use these haunches as a prop for erection? We needed to be thinking about how we were going to get the thing across. Another important decision, setting the bridge elevation. Here you see the river levels and how low things were getting. Here you can see the 1 to 100. It's almost touching the wood there. We were working with Fussy Parks Canada and the town on the one hand, and the hydrotechnical engineer on the other. One party pushing us down, the other pushing us up. And we were stuck in the middle with an ever more slender structure. And finally, the incredible environmental challenges. We had to almost pretend there was a skyhook dropping this thing in. We needed to do a full environmental protection plan and hired an environmental consultant and wildlife biologist to help us, all driving us toward touching lightly. Now let's get to the interesting stuff. The structural diagram itself is quite simple. But because the timber arch is so slender and shallow, it leads to all kinds of issues, like nonlinear behavior, just the geometry, and also the reliance on the soil, which is nonlinear, and creep in both timber and concrete. We had to be thinking, of course, about snap-through buckling, the enormous thrusts, and not least was the challenge of solving the geometry. it had to be precise because of the configuration of a shallow arch. And finally, of course, vulnerability to vibrations. So let's first start with basic structural concepts. A simple bending member, but not very efficient. A shallow pure arch pinned at each side. An arch with full fixity. Then let's recognize we need to get the forces into the ground with piles. So we need to understand the soil properties. But then the connection to the ground will not be perfect. So we need to understand something about the connections. And we need to acknowledge that the thing needs to get into place somehow. So we chose to erect it in two pieces. And so we need to understand the stiffnesses of all the connections. But the complicated bits in all of this are getting some accuracy into each of the stiffness components we've idealized, like the connection stiffnesses. And with timber, this is a difficult topic. And then there are the other components as well. Why is all this important? Well, it's a very shallow arch. And there are always good reasons to get your model right. But normally, if you stay on the side of conservatism, all will be well. But here, there are two fundamental reasons to do what it takes to get the model close to reality, or it ends up keeping us up at night. First, the geometric nonlinearity. It was scary. We're talking inches, horizontal movement being critical. And excessive creep in the glulam and concrete could lead to large increased deflections. Also, we need to understand the connection forces in this redundant structure and get as close as possible a prediction of the vibration characteristics. So let's look at our modeling approach. First, the nonlinear effects. The shallow arch low displacement. Secondly, as I mentioned, the soil. And then glulam creep, parallel to grain, and concrete cracking and creep in the piles. So we'll talk about those things. And we wanted to study our stiffness assumptions in all of this to understand how they would impact various aspects of our design, especially impact on deflections and all. We also thought about collapse prevention. It's in a non-seismic area, but what if the abutments were to, for some reason, move? And so we satisfied ourselves that at under 110% of the dead load in that very unlikely and really non-designed for event, could the bridge perform, even if there were large deflections? And so the sensitivity study chart you see here, we're inputting various large variations in the stiffness assumptions that we were making on the various components and seeing how it performed under those. Well, here's the computer model and some of the things we considered. And in it, we treated the pile cap itself, which was 5 feet thick and I think 30 feet long by 18 feet wide or something like that. So it's a big mass of concrete embedded in the ground. Treated that as a rigid body. We, as I mentioned, we had to think about the connection stiffnesses. We had to think about how to model the glulam arch itself with its steps, and how to deal with that very complex connection between the arch and the abutment. Let's look at the components. The elements are few, but quite complex. double glulam girders on each side, and you see the haunch elements anchored to the abutments. The steel diaphragm trussing, which connects the girders, and the timber decking and guardrail system. First, we'll talk about the glulam girders, which we stepped and tapered. Why steps? Why not a smooth curve? Well, creating a smooth curve in a long piece of glulam is very expensive, difficult to get right. Also, it doesn't respect the way glulam is made in distinct layers. Stress grades strongest at the extremities. We needed to overlap the T-lams. Care needed to be taken in the layout. The haunches made of weathering steel. And we built them up out of eye sections, welded together for composite action. But it was a very complex welding, and we were in the whole process trying to preserve the visual appearance as well. These would get cast into the concrete pile cap like that. And here you get a better idea of the complexity of that haunch, which was prefabricated as an entire unit and shipped to site. It also has paired members and the stiffeners linking the pairs. There's a side view showing how the glulam girders were anchored to the haunch with both straps to create fixity and vertical rods to tie it down to the haunch. And there you see it in the 3D view. And the abutment system with cast augured 1.1 meter diameter piles. Now, this pile type was chosen very carefully because of proximity of the river and the town and the environmental sensitivities, and they needed to be big and stiff. This was a very tricky procurement, which I was involved in great detail. It had a lot of risk. The glacial till had boulders in it, so there were unknowns involved. And being right next to the river, the likelihood of needing tremie concrete we had to plan for. And the piling company was only willing to take on a part of that risk. So we needed strong quality assurance. We need to really understand what was going on with the piles. We had to know we could count on the bending stiffness. And so you see here the concentration of rebar in the piles is higher at the top where the bending moments are the highest. We'll get into that. And finally, the diaphragm steel. It links the two pairs of glulams to offer buckling stability plus overall lateral resistance. Let's talk a bit more about the nonlinearities. First, the geometric. It's a principle of leverage. If you had a tall arch, the large lever arm to resist the global moment versus a small arch with a small arm. In this case, a small horizontal movement at the abutments results in a large vertical displacement in the middle of the span. Kind of like those things your professor told you to ignore as unimportant second order effects. Well, this is one of those situations where you needed to pay attention. And with the soils, most of the time you don't care how the settlement happens. The geotech just tells you maximum settlement of 3/4 of an inch, and you don't think about it. But soil is usually nonlinear in its stiffness behavior, and that is the case here. The geotech calls it the PY curves, the nonlinear pressure versus displacement curve. It changes with depth too. Well, you can put this into the structural model. Here we have plugged in the soil nonlinearities into the overall model. We were given them for each pile, and the soils program actually takes into account the proximity of the other piles. So it's quite accurate. Remember, we were trying to get as close to reality as possible with our model. We need to understand it. It's critical. And here are the results of our analysis for the piles taken from the global model. You see, as expected, that you get both shears and moment reversal. And note the moment is highest at the top where it's fixed into the pile cap. Let's talk a little bit about creep. Sorry. Yeah, in timber, it's a well-known thing that timber parallel to grain also creeps. But in this case, it's not a big factor because it's largely a problem where the moisture content is high, and in this case, it's quite low. But we did account for it when setting our elevations. And the concrete creep effects and the stiffness loss in the concrete in the piles due to cracking. It's your old eye crack versus eye gross, and we found that under service loads, it didn't crack, and so we were able to get most of eye gross in the model, but under ultimate it did. Let's look at the connections. You saw this earlier. So much going on here, both structurally and for construction simplicity. Here we are showing the strap connections which fix the girder to the concrete. Here you see how the girder thrusts into the end bearing plate and the rods which tie down the glulam to the haunch. You see here the bearing in here, and then these tie down rods which were pre-stressed. I'll show you that a bit later, pre-stressed against these spring plates we had at the top to account for glulam shrinkage. But we need to understand the impact of the highly concentrated force at the end of the beams. With timber, you cannot assume connections are infinitely stiff. And so we did a localized finite element model to understand the behavior of the stresses also through the beam, but get an idea of the stiffness of that joint through that transition from a highly stressed bearing condition at the end here and how it distributes beyond that. And we modeled all this in the computer program. And this is in the center where the two bridge sections were connected. And this was the key to erection simplicity. And this is the final model, accounting for all the factors we discussed. We found that the arching action took 74% of the global moment. And this was the result of the buckling analysis for the first mode under ultimate loading. Now let's move to the site, which was already in action while we were finishing our design work. One of the advantages of design and build is that construction timing can be optimized. I wanted to pop this in here just to show how I keep my engineers and project managers accountable. My project schedule at a glance. And anytime they come to my office, I pull out my cheat sheet and ask them, how are you doing? Well, here's a simplified version of the very complex scheduling program that they use, but these are the broad targets for the project. So we are basically in less than a year going from design right through erection completion. The only thing outside this, which we toyed with over the course of the summer because they didn't actually want to open until September, when they had the grand opening. So was the tune mass damper installation. Piling tender was in September for a December install prior to frost issues. As mentioned, very tricky, with the risk that the concrete cross-section could be compromised by river water and soil caving. We needed a very experienced quality contractor as well as tight QC, just to ensure everyone knew what was important. And it was a good thing we did that. It was a great exercise. We by fully understanding in concert with the piling contractor who and you're both sort of tugging and thinking about risks, but it turned out great. All that forethought was worthwhile. Here's the Bower rig which installed the cast augered piles. And we did need Tremie, so the decision was correct. And we also needed to find a way to dispose of the dirty, displaced water. So let's talk about pile QC. This is what they call thermal integrity profiling. It's probably the latest and greatest in, how do you find out what's actually going on down inside the pile? It's the most expensive but most accurate means of ensuring the piles are sound throughout their height. It works by installing wires and logging the temperature gradient as the concrete cures. Now, in the course of this, we actually did find one pile that was suspect, but it ended up in a non-critical area. Here we have the haunch being fabricated. Note the 35M bars in the top right-hand photograph, which would be cast into the pile cap. So here we are on site installing the haunch into the formwork of the pile cap. And we did the piling before winter, before the frost, and this allowed also an early start with the formwork in the spring. Actually, I think in late January or early February, get going. And here's the haunch ready to receive the bridge section. Let's talk about the glulam. Here are the glulams being laid up in the glulam plant. And almost all of the fabrication work, the coating, was done here. You want to protect that wood in a shop-controlled environment. And you want to protect all of it, including the cuts. This is the plan for assembling the bridge sections by the river on site. The 40-meter beams were brought in using a truck with a steerable rear axle. Can you imagine these things? 130 some odd feet long, traveling down the highway. Well, especially in Europe. Here's the assembly of the south section. You see one pair of beams already set up, and then the other ones are going to be laminated to either side of the ones that are there already. Moving to the north side. And here you see the stitching of the diaphragm steel into the insides of the Glulam girders. These are the cuts for the mid-span pin connection, and they were the only site cuts in the Glulam. We saved that for the site because we actually wanted to measure actuals, bearing plate on the north side to bearing plate on the south side, and get the survey results of the actual before we made these final cuts. As I mentioned, the geometry is critical. And here's the midspan connector with the installed into the tips of the bridge sections. Well, this was the day I had been planning for, cogitating over, waking up in the middle of the night with ideas. The geometry was critical, and tolerances were just too tight. We're talking, we had just, millimeters that we had to be thinking about. And we needed a slick way to bring the two sections together. We did not want the workers out there fiddling with the connections while the beams were still on the free hook. Here's the site staging plan. The cranes with their outriggers. We ended up we were able to put the critical outriggers right on top of the pile cap. And the piles and the timbers, the bridge sections here on each side ready for installation. This is our erection procedure. And I'll describe that in a little more detail when we get to the pictures. But so our idea was to put the south bridge section in first with the tip slightly high, cinch the haunch end tightly into the bearing plate on that side, cinch the bridge section down with the vertical rods to the haunch. Then we could allow the workers to proceed onto the span because we've got it fixed. Next, placing the north bridge section, engaging the central pin to the south section prior to the final lowering. So you can imagine that the north and the south section are hanging there. The north section is not engaged yet with the abutment. We do now a test lowering to engage with the shim pack at the north abutment bearing plate. And then we measure the center span elevation to achieve the target elevation, and then add shims as required at the north abutment. And then finally confirm the target elevation. So here's the start elevation, the target elevation, and then the final elevation, which we calculated, and the final was going to be after the creep was, and all the slack was taken out of the structure. Here we are on site. Here's the plan with the cranes. They were about 35 metric tons each. Then here we are cinching the girder to the south abutment. And we also had a come along in the center so that once it was close to being engaged, we could just pull it into place. And here's a little video which captures most of the erection process. Yeah, so and here we are with the south bridge section all outfitted and ready. You can see the straps in the center ready to receive the north section. Flying the section into place. set right. And here we are cinching that south section into the abutment and locking it down. Bringing in the north section. The idea was to, as I said, to lock the south section to its abutment first so the guys could safely scramble out there. And then we would bring the north section in, but instead of locking it to the abutment, the end would float while we locked the pins in the middle. It worked perfectly. We had this thing in a matter of hours. Here, the guys are engaging the bridge sections. And so in this strategy, we could much more easily adjust the shims and the bearing to get the midspan height right. And in fact, it only took one iteration. We measured things so carefully, it surprised us actually how quickly it came together. And, you know, I was down actually because there's some shims that needed to be set and got right between the timber and the haunch. So actually, the client and I were both down there helping adjust these shims a bit, the shims that to bear the timber on the over the length of the haunch. And while I was there, and we were lowering the final weight off the cranes, I was standing there and watching the section come into bearing, and we were monitoring the load transfer from the crane to to release the thing into and activate the thrust. I heard some loud noises. I thought, what was that? It dawned on me all of a sudden that I was hearing the noises of all the slack coming out of the system as the shallow arch came into full compression. And it manifested itself in a whole series of creaks and groans. It worried me at first, and then I understood what was going on. And so it found its home. So someone happened to be up on the adjacent mountain and taking photographs. So we captured that too. And so here are the spring plates, which allowed us to pre-stress the beam down to the haunch. And this accounts for future shrinkage in the deep glulam. There wouldn't be much shrinkage, but we wanted to account for it. And here are the straps being fastened to create the fixity to the abutment. And you may have noticed when the south section was being erected, the hanging rolling platform that we had already mounted on the section during the erection process. And we used this to get the guys access to the tension straps. And we just kind of rolled it over so they could get in underneath here and fasten the tension straps. This is for the moment fixity at the center. Here's a quick video of the erection. And we're almost done. We'll talk about vibration a bit. Okay. So talk a little bit about the deck and the guardrail system. We prefabricated the deck sections so they could be removable in the future. And there you get an idea of the guardrail system too. So let's talk about vibration quickly. The first vertical was measured at 1.9 hertz, which is right in the range of walking. And the first torsional was at 2.4 hertz, which is right kind of in the range of jogging. So we had to think about both the sensitivities to both of these. So we created a homemade tune mass damper, which is suspended from the bridge underneath, and it's 3,000 pounds. And it actually was tuned and configured to address both. The vertical was, the walking was handled through vertical motion of the damper, And the jogging was handled through torsional, which is a sideways movement of the damper. Great. And achieved huge reductions. We actually felt it. We felt it before and we felt it afterwards. And there were huge reductions as a result of the damper. Here's the testing going on. And if you look closely through the gap there, you can see the damper going sideways, back and forth there. Okay, and finally, here's opening day and the completed structure. Yeah, and I want to thank you very much.